So this is the class video for Friday, November 13th, 2020. So just a reminder that on Monday we'll have our Mass Insight session with Sue Biggs. Homework is to complete the 3.11 to 3.12 problems due by Sunday, and Unit 3 test corrections are due on the 20th. And then you'll post a final picture of your alum crystal by Tuesday, the 24th. So the opener was to figure out if you wanted to do absorbance spectroscopy on a blue solution, what's the best color of visible light? And that would be orange, because here we have blue over here, and that's the color of our solution. Make that a little bit. So opposite there, okay, this color should be absorbed most, because here the blue solution absorbs the orange and then transmits all that blue color to your eyeballs, and that's what you see. So here again, for our color of solution versus color of light absorbed, so our gray arrow up is over the green, because that green color is most absorbed by red, okay? That's most absorbed by red. And then the yellow thumbs down is on the red, because a red solution transmits this the most, okay? So this is least absorbed by red. So this video right here, you can click on that on the slides if you want to, and re-watch this video, but it goes over the solutions and it puts them in the spectrophotometer. And here's a couple of the solutions. Cobalt nitrate, this pink, is absorbing strongly in the green. So at the maximum absorbance, we're in the green area. Potassium permanganate, this purplish color, similarly, okay, absorbing in the green. And we can see that a concentrated solution has a higher absorbance than a more dilute solution. And again, here you can see the complementary color kind of in between green and yellow. And this Fe+2 solution, kind of an orange color, is absorbing strongly in the purple. Zinc is colorless, so it doesn't absorb anything, right? It transmits all the light, which combines into white light. And so all we see is no color, okay? Because white light is the combination of all the rainbow colors together, and we see no color when they're all combined. This nickel solution is sort of a greenish, so we're seeing some absorption in the red area, but there's also a little peak over on the purple, and that may have to do with some other transitions in nickel. I'm not quite sure. I should look those up. This copper solution, okay, is blue, so it absorbs on the red. So if we wanted to indicate the best wavelength to measure the absorbance, we'd measure it like right here. Okay, this is the maximum absorbance for the copper solution. So that's going to be kind of like in the 800 range or so nanometers would be the best place. All right, so then we tested a couple food colorings in the spectrophotometer to see what they looked like, and it was fun to see those. Here is just a schematic of a spectrophotometer. We got white light coming in. The monochromator splits the light into different wavelengths. It's basically called a diffraction grating with little lines, and it splits the light into different colors. And then this aperture narrows the light, and then the light goes through the cuvette with the sample, and then the light that's transmitted goes to the detector, and the detector goes to the computer, which translates this transmitted light into the absorbance. Now, when you were doing your cell phone, your detector was the cell phone right here. And your cell phone measured the transmittance just like the detector did. However, you had to be the computer and change this transmittance into the absorbance. A spectrophotometer does that all for you. So in order to make the standard curve, we start out by making a stock solution in the lab. And in order to make a very accurate volume of solution and know exactly what the volume of our stock solution is, we use a piece of equipment called the volumetric flask. It's very accurate, and this is a 10 milliliter flask. And you can see that this mark right here indicates that you have exactly 10.01 milliliters right at this mark. If you can make the meniscus, okay, so here's our mark right there, just like over here. And if the meniscus of water, okay, water makes a meniscus with glass. If the bottom of that meniscus lines right on top of that, ends up right on top of that line, then you have exactly 10.01 milliliters. Okay, so this curve that water makes with glass is called the meniscus, and the reason why it clings on this side is because the water is attracted to the glass, so it makes this curved shape right there. So we use our volumetric flask to make our stock solution, and the steps are, first we have to figure out how much solute we need for that volume of the volumetric flask. So basically, right, we use the molarity equation to calculate the moles needed for a certain volume and for a certain concentration that we want. And so we calculate our moles and we change that to grams using the molar mass. We weigh it out on a balance. Then we put the solute into the volumetric flask. So put that solute in and add enough water, and we wash all of the solids down as best as we can. We add enough water so that we can dissolve the solute in the water, about half of the water. Then we swirl, we mix that solute in as thoroughly as possible so that all of the solute dissolves. Then we add distilled water until we reach exactly where that mark is. And then this step is really important too. You have to cap the flask and make sure to invert, meaning turn it upside down several times to mix this solution thoroughly. You don't want a bunch of dense solution on the bottom and watery solution on top. So you have to make sure to invert your flask. All right, so then from your stock solution, we have to dilute it to get the other concentrations that you need for your standard curve. So we're using our dilution equation, M1V1 equals M2V2. So we can use, right, the initial amount of our stock, right? This is kind of the stock solution side. If we have 1 molar stock solution and 10 milliliters of it, we multiply those and we get an amount of moles. Don't worry too much about millimoles. It's the same as moles. It's just thousandth of a mole. Okay, that's what you get when you multiply molarity and milliliters. So the moles, even when you add water, the moles stay the same. So that 10 millimoles equals some concentration times the new total concentration here. So we just have to do this M2V2 side and solve for the molarity, and it's 0.5, which makes sense since we started out at 0.1. We changed the volume, V1 to V2, doubled. So M1 to M2 halved, okay? These are inverse relationships, so this went up by 2, and so then the molarity went down by 2. It halved. It's half of what it was. And then so we can use that dilution equation to figure out the the molarity of these different diluted solutions by using the molarity equation. And you can watch this video again if you still need some extra help figuring out the concentration and how to do the dilutions. So here for an example problem, if we have a stock solution of 0.01 molar, that's our M1 here. Our V1, our stock solution right here is 7 milliliters. So that will equal our M2, which is our unknown. And our total volume after dilution is 10 milliliters. So then we can solve for our new molarity by dividing both sides by 10. Okay, so 0.01 times 7 divided by 10 gives us a new diluted molarity of 0.007 molar. Okay, so that is the concentration of this diluted solution. So then if you take a look, these is it's 5 and 5. It's going to be just half of this. This is going to be 0.005 molar. This is going to be the opposite of this first one. It's going to be 3/10 as weak. So this is 0.003 molar. And here we have 1 milliliter of stock, 9 milliliters of water. It is 1/10 as strong. This is 0.001 molar. So I hope you can see how that dilution works itself out in just in a kind of a qualitative way as well. All right, so this is a similar problem again here, and here's the solution right here. We get a molarity of 0.00. This is the answer for the first one. Here's another example right here. Solve in the same way. M1V1 equals M times V, and we find the moles. We set it equal to our new molarity times the total volume, and we can solve and get our molarity of our diluted solution. So after making all these diluted solutions, now we need to make the standard curve. So we'll measure the absorbance of each of these known concentrations and record them. Then once we have our standard curve, we can get the concentration of our unknown solution after we measure its absorbance. And then we can figure out the mass of our colored species in our unknown and using our stock solution. So here, when you plot absorbance versus concentration, hopefully the line is straight. If you did your major solutions well, you should get a nice straight line for the standard curve. And the absorbance is going to be directly proportional to the concentration, because Beer's law is absorbance equals epsilon BC. Epsilon is the extinction coefficient, the molar absorptivity. This is a constant for the solution. This is the path length. Well, ideally, we don't change that. We take the absorbance reading at the same distance every time. And so this is our concentration, okay, and our absorbance. And so you can see that the absorbance is directly proportional to the concentration. So our graph right here is just a relationship between the absorbance and the concentration. When one of these goes up, the other one also has gone up. And just a reminder from algebra, y equals mx plus b. So here, y is the absorbance of the food coloring. Here's our m and our x plus our b right here in this equation. So using this equation, I can find the concentration of a solution within an unknown amount of yellow food coloring. This is my graph for my yellow food coloring. So I can put in a unknown solution that contains yellow food coloring, and if I measure it as 0.35, so for example, if I had some yellow Gatorade containing this yellow food coloring, we could calculate the concentration using our equation, and the answer would come out to 164%. The way we did this was I stuck in 0.35 for Y, so 0.35 is our absorbance. So then we have 2.2 times 10 to the minus 3 times x, and then this is minus 0.0122. So I can just add 0.122 to both sides, do my algebra. Okay, and then I can divide both sides by 2.2 times 10 to the minus 3 and solve for x. So I would have to, this would cancel out. And so we would have to do over here 0.35 plus 0.0122 divided by 2. Oh, let me move that out of there. Okay, divided by 2.2 times 10 to the minus 3, and that gives us x, which is our concentration. And that comes out to 164%. All right, so you can do the same thing for this other example. This is an example of copper in different standard curve solutions here, known concentrations and absorbance here. And we can take this unknown brass solution that contains an unknown amount of copper, and read the absorbance from our spectrophotometer, then use the equation, plug 0.726 in for the absorbance, and solve for x. And then when we go ahead and actually calculate, again, we're going to stick our absorbance for our unknown solution in here. So 0.726 equals 13.4x minus 9.93 times 10 to the minus 3. And we solve for x, and the answer comes out to 0.0549 molar. All right, so a couple of the post-lab questions. Oh, we need to go back. If you put a smudgy fingerprint there, what happens? Is this going to cause the same absorption of light? Well, no, because now some of the light can't get through because there's a big smudgy fingerprint in the way. Some gets blocked or scattered. So it looks like more light is absorbed by the solution. So then if it looks like, if the detector detects more absorption, then when you go to calculate, right, you get a higher concentration than what is actually in the solution, and you get a higher molarity, which is inaccurate. Okay, so your calculated concentration is too high. All right, now if Ferdinand adds too much water to the 75 solution of food coloring, what happens to our standard curve? Well, our standard curve usually looks something like this. Well, now this 75% point is going to be like down here. That makes this line that we fit have a lower slope. It'll be flatter. Okay, so then the calculated concentration for the unknown is going to be too low. All right, and then we had a Lab 4 group quiz. I talked about some reflection questions, and then we went into 3.11. Actually, this is 3.11 and 3.12, both of these. So we started talking about spectroscopy. What is spectroscopy? Well, it's this amazing study of the interaction of light with matter. This is the way that Scientists have learned to see what's going on with that invisible stuff that causes all that, macroscopic phenomena, the things that we can interact with that we see happen, right? A way to see this and to explain those phenomena that we actually see in the real world. So here's some light, and light is also called electromagnetic radiation. So light is both a wave and a particle. Here is the wavelength when we go from the crest, the top of the wave, to another top of the wave. That's called the wavelength, that distance. Okay, so the wavelength is usually, you need to make sure that it's in meters. Every single light wave, no matter what type of light it is, travels at the speed of light. And there's our speed of light, 3.00 times 10 to the 8th meters per second. So if we want to investigate atoms and bonds that are 10 to the minus 10th meters, okay, very small, hundreds of picometers, we have to use radiation whose wavelength is about the same size. Otherwise, it can't interact with things that small. So here, if we want to show the light wave with the largest frequency, I'll just go to the answer here. So the blue square, right, this is the larger wavelength, but the red circle indicates that this has a larger frequency. And I'll talk about where that comes in. So the frequency is how many wavelengths, okay? How many wavelengths fit into a unit of time. So if you consider this to be like here seconds, and seconds pass by, you can see that more wavelengths fit in B than in A. So the frequency is higher here, but this has a shorter wavelength. Shorter wavelength, higher frequency. This has a larger wavelength and a smaller frequency. Okay, so the relationship between the wavelength and the frequency is an inverse one. Larger wavelength, smaller frequency, and the opposite is true too. Smaller wavelength, larger frequency. All right, so then that gives us the electromagnetic spectrum, which contains all the different kinds of light. So here, the light with the most energy is going to have the highest frequency and the shortest wavelength. Okay, so high energy is on this end. And if you look at the types of light, like X-rays, you do not want to get blasted with X-rays or this gamma ray, which this looks like something out of Star Wars. Doesn't really look like that. Can't even see it. And UV rays, we know that that causes sunburns and skin damage. So we're more familiar with these things being pretty harmless, right? Microwaves and infrared is related to heat waves, and radio waves go through us all the time. Visible light we're very familiar with. That doesn't damage us. Our eyes can sense it. So as we go down here, we're getting to longer wavelengths, low frequency, lower energy light waves. So you should explore this PhET simulation. The PhET simulation shows a couple cool things, which I'm going to show you in a second. And we are going to investigate what do these different types of light do to water molecules and other molecules. So let me cut over to that now. Okay, so here is the PhET simulation. This one is called Molecules in Light. So first we'll start off with a carbon monoxide molecule, CO, and we'll start with microwaves, and we'll start shooting some microwaves. Well, look at that. The molecule starts to rotate when it absorbs microwaves. Let's try infrared radiation. With infrared, the molecule seems to be vibrating if it absorbs infrared radiation. With visible light, nothing happens. UV light, again, nothing happens. The molecule does not absorb visible or ultraviolet light. Okay, so let's go and do the same tests with nitrogen. Let's shoot some microwaves at it. Nothing. Let's try some infrared. Nothing again. Visible light. Nada. Ultraviolet, UV. Still nothing. So for nitrogen, nitrogen doesn't absorb any of these types of radiation. And if you look at the difference between carbon monoxide and nitrogen, the difference is carbon monoxide is polar. It has a dipole, it has some difference in charges, and that's able to allow the molecule to interact with the light and absorb it. Nitrogen has no dipole. Turns out molecules with dipoles can interact with microwave and infrared. Let's go to ozone here. So if we shoot microwaves at ozone, oh, in fact, it broke apart. Okay, so let's shoot some infrared radiation. Again, we see some vibrations happening. Okay, so ozone is a polar molecule again. It can interact with both microwaves and infrared light. With visible light, again, nothing happens. Ozone is not colored. It will not absorb visible light. UV radiation appears to break the molecule apart. And we kind of know this because, right, we know that ozone protects us from the UV radiation, right? There's an ozone layer in the atmosphere, and ozone molecules absorb UV radiation and reduce the amount of UV that comes down to the Earth that way. Okay, one more thing to show you with methane. Methane is a greenhouse gas. Okay, it's transparent to ultraviolet. No changes there. Again, visible light, no changes. With infrared light, oh, it seems to absorb infrared light. And we kind of know this as a greenhouse gas. Methane absorbs infrared and radiates it back. It's one of our greenhouse gases that is causing temperature rise in the Earth's temperature. With microwaves, there's no interaction because it's not able to change its dipole by rotating. Okay, so it seems that microwave radiation, what does it do to water molecules? It makes them rotate. Infrared light to water molecules, it makes the bonds vibrate. What happens when you shoot visible and UV light at water? Nothing. These don't interact with water. Water is colorless. So here I've just labeled the different types of light with the types of transitions that can occur in rotational energies. So these transitions happen, right? The rotational energies can change using microwave light. Infrared light can cause transitions in vibrational energies. Visible light can cause transitions in electronic energies. through the absorption of visible light, and then UV radiation can cause transitions in electronic energies as well. X-rays and gamma rays basically cause complete removal of electrons from atoms. All right, so this problem here asks what type of energy transitions are observed in region Y. So here region Y is the infrared. So we would expect vibrational transitions to occur in the infrared. Region X will cause transitions between electronic energy levels, and region Z causes transitions between rotational energy levels. So we want to make sure we select the right tool for the job, depending on what sort of energies we want to examine in our molecule. So these, again, are labeled with the types of transitions that occur, depending on the type of light. Now, these, right, mass spectroscopy is a different sort of spectroscopy that we did earlier, and that allows us to separate different masses or isotopes in the sample. Here, we're actually using matter, right? We're throwing in matter and we're probing matter. And with PES, which we talked about earlier, we're sending in X-rays and we're getting out electrons. Okay, so this relationship between the wavelength and the frequency comes out to be this constant speed, lambda, this wavelength in meters, and I'll spell that out, lambda, okay, is the wavelength in meters. And this funny letter here, this is called nu. It's the frequency in 1/seconds or hertz or seconds to the -1. So therefore, C equals lambda nu, the wavelength, times the frequency, since all light goes at that speed. So here's an example. We want to calculate the frequency of violet light that has a wavelength of approximately 400 nanometers. And 1 nanometer is 10 to the minus 9 of a meter. So what we want to do is use the equation, C equals lambda nu. The question asks us to calculate the frequency. So let me solve for the frequency by getting it by itself. Divide by lambda on both sides. So nu equals C over lambda. So I can put in for C 3.00 times 10 to the 8th meters per second and divide that by my wavelength. It's 400 nanometers. So let me do a quick conversion here. 400 nanometers, okay? And I want to put my 10 to the minus 9 meters on top because I want to cancel out my nanometers. Here you go. Okay, so that's going to equal 4.00 times 10 to the minus 7 meters. Meters cancels out, and we get an answer, which is on the next page, of 7.5 times 10 to the 14th seconds to the minus 1. So these equations are on the top of your first page of your equation sheet right here, and we'll talk about this one next. But here's your wave equation, your light wave equation, and it defines what these different things are. Energy is going to be in joules. Frequency, again, it's going to be 1/seconds or hertz or seconds to the minus 1. These are all equivalent. Wavelength has to be in meters for this wave equation to work. And then here are some constants. The speed of light is right here, and Planck's constant is up next. Here's another example, okay? So I'll just go to the solution here. This is what is the wavelength of electromagnetic radiation having a frequency of 5 times 10 to the 12th hertz. Okay, so I want to underline some things like here's what I need to find, here's what I'm given. So I'm going to use my wave equation again, C equals lambda nu. And I want the wavelength this time, so let me get the wavelength by itself. So lambda equals C over nu. Let me plug in chug here. For C, I'll put in 3.00 times 10 to the 8 meters per second. And then for nu, I'll put in 5.00 times 10 to the 12 hertz, which is the same as 1 over seconds. I can see that that cancels out. And I can solve, and my answer is 6.00 times 10 to the minus 5th meters. Okay, and the type of radiation would be infrared. It's right in between here somewhere. So is light a particle or wave? Well, turns out both. It sometimes acts like a wave. Like you can see here, if we send in a light source and we have two slits and the light goes through here, the light interferes and we get these interference patterns on a screen where the waves combine constructively. That means they add together and make a larger wave, or they cancel each other. They add destructively and they cancel each other out and you get these dark spots. So here it's acting like a wave. However, there are cases like this example right here where the light acts like a particle. We're going to talk about this example next. So this is called the photoelectric effect, and Max Planck was the one who received the Nobel Prize for discovering that light comes in photons. The energy of a photon equals h nu is what Max Planck discovered. This is, by the way, this is the energy of one photon, just one. So E is the energy in joules for the photon. H is something called Planck's constant. He found that the frequency and energy were related by Planck's constant. So, and that's this very tiny number here, 6.626 times 10 to the minus 34 joules seconds. And then nu again is the frequency in hertz. Later on, very, very soon after, Einstein receives the Nobel Prize for explaining this thing called the photoelectric effect, which basically had led Max Planck to make this conclusion about the photon, but Einstein was the one who actually explained what was happening. So what is happening in the photoelectric effect? So in the photoelectric effect, we have a metal here. A metal has many electrons in our sea of electrons. They are bound to the metal, the positive part of the metal. And when we shine light on this metal and slowly increase the frequency of the light coming in, slowly increase the energy, in the beginning, we don't see anything happening, but at a specific photon energy, all of a sudden we see electrons popping off. And we find that each of these light packets, these photons, corresponds to one electron popping off. So if we send in 3 photons, we end up with 3 photoelectrons. So basically at this very specific energy, if the photon is equal to the binding energy of the electron pops off and just sits right there at the surface of the metal. If we put in light energy that is greater than the binding energy of those electrons, then the electron, the electron gets taken out, removed, right? Some of that light energy goes into breaking the electron's bond with the metal, and then anything above, anything more than the binding energy turns into kinetic energy for the electrons. Okay, so basically this energy of the photon is equal to h nu, and it's equal to the binding energy of the electron plus the kinetic energy of the electron. Now, the AP exam will not test your explanation of the photoelectric effect. However, it will use the photoelectric effect in problems. So it's a good thing to just kind of have some idea of what it is, and so that it's not completely foreign when it comes when you come across it. All right, so then we went to these practice problems here, and this is homework. We didn't get to going over to FRQs, and I knew that a bunch of people hadn't gotten a chance to do these, so I will grade those once they're turned in, and I will post the answer key on Monday. So here, let's go to these 3.11 to 3.12 practice problems. I'll do a couple as examples. Okay, so number one on the practice problems, you can see here that there is light coming in. So these are light waves coming in. This is a piece of metal, and we have electrons shooting off, and basically the text tells us that the diagram above represents a photoelectric effect for a metal. And when the metal surface is exposed to light with increasing frequency and energy of photons, electrons first begin to be ejected from the metal when the energy of the photons is 3.3 times 10 to the minus 19th joules. All right, and the question, it should have read, what is the frequency of the light with photon energy 3.3 times 10 to the minus 19 joules? I'm gonna underline a couple things. I'm going to try to find my question and my givens here. So this is just a kind of strategy to set up your problem solving. It might be helpful. It might not be. If you choose to use it, then great. If you don't need this sort of frame, you don't have to use it. Just a example and something that might help some people. So just doing an example with this. So our given right here, okay, we want to find information that is given to us. So we are given this photon energy. So I'm going to write my E equals 3.3 times 10 to the minus 19 joules. And I know it's my energy because it says it's energy and also it's joules. And I also want to find my question. What is the thing that they're asking me for? And that would be the frequency. So they want me to find the frequency. Okay, next step in my frame here, I want to figure out what equations and constants I need. So I look here at the given in the question. I have E and frequency. Do I have an equation that relates these? Yes, that would be E equals h nu, where frequency, remember, is nu. So here I have my E, my nu, but I need H, and so I looked that up. That's 6.626 times 10 to the minus 34 joule seconds. Planck's constant. My strategy will be to plug in for my H, plug in for H, and for E, and solve for my frequency. So let me do that now into my equation. So I'm going to plug in E here, 3.3 times 10 to the minus 19 joules equals, I'm going to plug in H in there, 6.626 times 10 to the minus 34 joules times seconds. And my unknown is my nu, so I'll leave that alone. And I'm going to solve for nu. So I need to get that by itself by dividing both sides by Planck's constant. All right, so then I can solve here for frequency, and my answer is 5.0 times 10 to the 14th 1 over seconds for my frequency. Or I could have put that as seconds to the minus 1, or I could have called that hertz. So that's my answer. Always good to circle your answer. I'll do one more example. Number 2. Whoa, look at all this text. The AP exam loves to give text. Now, for this problem, actually, you don't have to read this text at all to do this problem. However, if you go to a later part of this problem, you do have to have read the text to understand what is happening. But for this part of the problem, we actually don't need to read this text about the the visible spectrophotometry. So let me just skip that for now, but basically this question has to do with Beer's law, but it also relates part of the stuff to spectroscopy and equations. All right, so we're going to go down to the actual thing that we need to answer, and it says a wavelength of 510 nanometers corresponds to an approximate frequency of 6 times 10 to the 14th seconds to the minus 1. What is the approximate energy? I'm going to box that. That's my question here, of 1 photon of this light. So here again, let me put down my givens. Given, I got 510 nanometers, and it tells me that's the wavelength. And then it also gives me 6 times 10 to the 14th seconds to the minus 1. That's my frequency, and it tells me that. And then my question is, it says, what is the approximate energy? And I boxed what I need to find. So I need to find energy. That's going to be E, and I know that that will be in joules. So let me go and find an equation that's going to allow me to find E. So I see that I have a wavelength and a frequency, but I need something that relates E to one of these. And so I'm going to be using my H E equals H nu equation again. So I'll use this equation. I need Planck's constant, which is 6.626 times 10 to the minus 34 joule seconds. Okay, my strategy will be to plug in for H and nu and solve for E. Okay, so I'm solving for E equals my H 10 to the minus 34 joules seconds. So there's my H times nu, which is over here my given, 6 times 10 to the 14 seconds to the minus 1. This will cancel out, and I can multiply those two together, and I get 4 times 10 to the minus 19 joules. Okay, and I should box my answer, circle my answer, and that is the solution. Okay, I hope this was helpful. Let me know if you have any questions.